Well, welcome to June. Hopefully, you guys all had a lovely Memorial Day weekend here in the Carson Tahoe area. It was very beautiful. Um, but our plan here today in physics is to keep talking quantum numbers. There's one more quantum number I got to tell you about. And then we'll talk about some of the consequences of all of these quantum numbers. And specifically, we're going to start looking at how the whole periodic table kind of came to be, like why it's structured the way that it's structured, and how we know so much about it, and like historically, kind of what happened. And then we'll also talk about just some kind of interesting things that are byproducts of this quantum world, things like lasers, fluorescence, things like that. So we're just going to kind of, today's our plan is to wrap up the quantum numbers, just so we've got all of that, and then we'll start moving into the structure of matter. So what it means for like what the nuclei look like, what it means when we talk about metals, or when we have things that are conductors versus insulators, and we'll just kind of get to the what do all those things mean. So that's kind of the next big topic. And then after we get into the nuclear structure, then we'll start going smaller. So we'll wrap up this class in a couple of weeks with the talk of things like quarks and the like. So anyway, that's where we're kind of heading here for the next little bit. Before I take over and just start driving here, any questions you guys have? Anything you want to talk about from the last couple of classes, or the homeworks, or anything? Which just reminds me, I think I need to give you guys another homework set. Yeah, I'll get around to that.
There's chapter 7 due on the 3rd, so Thursday.
Right. But we're now in chapter 8, which is why I need to get you guys another one here. But I got a couple of days. I got some time. But any questions on the chapter 7 stuff? Are we good at this point? All right. Well, sounds like we're good. So let's keep talking quantum numbers. So I'm going to go ahead and share my screen. I'm going to go to the whiteboard here. And what quantum numbers have we talked about so far? What quantum numbers do we know? And I know it's been a while, plus it was a long weekend.
The principal, the orbital, quantum, and orbital magnetic.
Okay. So I was about to say, by my count, I think we have 4. Is that right? We have 3. Yeah. So we have N, which is the principal.
There's angular momentum, right?
Yeah. So the principal quantum number, and this one is the one that pertains to energy, right? So the N, it's really telling us how much energy something has. All right. So we have N, and then we had L. And this is I call this the orbital. Again, remember what these are coming from. These are coming from the 3 different dimensions, and really they're coming from the idea of spherical. So the orbital is pertaining to the theta. I call it orbital. The book called it the angular momentum orbital quantum number. And because that's actually what it is, or what it does, it's the angular momentum. And I'm going to put here from an orbit, even though we now know that electrons don't actually orbit. That was the original model, so that's how everything got named, right? So that's our orbital. And then we had M sub L. And this one, I call it the orbital magnetic. So that's the sub L, helps you remember that it's orbital. But it was a magnetic one because we call it magnetic because it showed up from looking at the, or something we saw when applying a magnetic field. The book calls this one the angular momentum projection quantum number. Okay, well, this is the Z component of the angular momentum. And so we saw basically from all of these that the amount of energy that we can have in an electron comes in discrete chunks. There is a formula, remember, it's all based off of n squared times that kind of baseline number. So energy is quantized, but then we also saw that angular momentum is quantized. There was a formula for that as well. Let me go ahead and put that up here real quick to remind you about that one. That the L was equal to square root of little l times L plus 1 times H slash. Let me go ahead and give you your energy here. It's minus 13.6 electron volts times n, or 1 over n squared. Sorry about that. And then for the this one for the orbital magnetic, we don't really have a formula for it. It's just telling us the different possible, I guess we do have a formula for it. It gives you the different possible sizes for your Z component. And so I guess we'll call this LZ. But it's just the multiplier of this ML times the H slash. Right. So basically we can have an orbital magnetic, angular momentum from the orbital bit that is horizontal. That would be 1 at 0. Or we can go 1, 2, we can go up a certain number. But that's just giving us the different kind of tilt to the angular momentum.
I have a quick question.
Yeah.
Do these quantum numbers make it to where we know less about the position of the electron because of the Heisenberg uncertainty principle?
Okay. Not really.
Okay.
Because we never actually measure this. Like, okay, so here's the deal. Let's say you have an electron. You don't know what energy level it's in, right? Like we have no idea what energy level it's in. We also don't know what its angular momentum is necessarily, and all that. How we find out about those things is when we see them change. Because think about this: when it jumps from one energy level to another, what happens? What's required, or required byproduct or whatever, for an electron to jump from a different n, let's say from n equal 4 to n equal 2 or something like that?
The radius needs to change, right?
Okay, so if it were actually in a orbit, the radius would change, even though we now have subsequently seen that because of the wave nature, right, that it's not necessarily in that orbit. It's most likely at that distance, but it could be anywhere. But what happens every time we have an electron jump from energy, like energy n equal 4 to n equal 2?
A photon.
Yeah, we always get the release of a photon. And so really, all we're going to know is when there's a change in energy, right? And this at least is a change in energy due to n. But there are also little steps of energy that are due to these other guys. So, and it's never like we actually measure that thing, that electron, because we don't even know where it is, right? So, but the more we know about its energy, or the more we know about its angular momentum, or its momentum, right, the less we're going to know about either the time spent in that energy state or its position, right? But it's not like we have an electron and we can just measure these things about it. We're always measuring really kind of byproducts. And if you think about that, okay, so it just released a photon. Do you still know that it's at that new energy level?
No.
No. Because who knows, maybe it released another photon that we didn't see, or it absorbed another photon and now it's at a higher level. And so, yeah, it's just one of those things that, and these things happen, and it happens very quickly, by the way. The amount of time that they tend to stay in those sort of energized states is not high, or any one state for that matter. They tend to bounce around. Anyway, so I would say yes and no. Right? Yes, obviously, the more we know about its energy, the less we're going to know about how long it stayed in that energy state. And similarly, the more we know about momentum, the less we're going to know about its actual location. But also realize that orbital momentum is not the same as linear momentum. So they're not the same ones for the uncertainty principle. So just make sure you keep that in mind as well. Even though we still call it momentum, it's a different kind of thing.
Oh, so specifically with the Heisenberg uncertainty principle, that applies to the linear momentum of it, not its
Correct.
angular. Okay.
Yeah, it's linear momentum versus position,
Got it.
and it's energy versus time.
Okay.
Those are the two forms for the uncertainty principle. But good question, and I'm glad you're kind of thinking that way, because those are the things that we do have to think about now. We can't just take that for granted like we did before. All right, so I think actually we've only talked about these 3 quantum numbers so far, but there was one more thing I wanted to remind you about, and that was the different options we have for these things. Obviously, n, it can take on any counting number from 1 on up to infinity. The greater the n, the closer that its energy gets to 0. Remember, this is kind of a funky thing. We're looking at it as a negative, where 0 would be the amount of energy in it due to the infinite state. And so as n drops, so does the energy level. It just drops negative. It's just a matter of scale, right? If we wanted to, we could say, well, the ground state is 0, and then increases all the way up to 13.6 electron volts as we go towards infinity. But the reason we don't do that is that 13.6 is unique to the hydrogen in this, because that's what we're building here. But if you were to look at other elements, you would see that they have different ground state energies, but they all have the same infinite state energy. So it's just one of those where it seems kind of funky, but the place where they all come together is out at infinity. So that's where we make it 0. Kind of like when we did absolute 0 with temperatures. That came from where all the gases were going to end up being at that same pressure with temperature, right? And then we had to backtrack it. It just happened to be the other direction. Anyway, so n is just countable. The L, this one, it can be 0, and it also is countable, but the maximum it can have is n-1. And that came from geometry, basically. Sorry, no, that one didn't come from geometry. That one comes from just the angular momentum measurements. But then the m sub L, it can be 0, plus or minus 1, plus or minus 2, and so on, up to and including plus or minus L. And that's the one that comes from geometry in order to get z components of these vectors The biggest the Z component can actually be is L. All right, so those were the quantum numbers that we have seen before. And they, like I said, they kind of correspond to the 3 dimension. Now, it turns out that there is another one that is what we call M sub S. So we had M sub L and we had M sub S. And this corresponds with another thing called S. So we're going to have M sub S and we're going to have S. Now, S is kind of a boring quantum number. But what S is, this is the spin angular momentum quantum number. All right, so I'm going to give you an analogy. I'm going to give you kind of a way that it was modeled, why it gets this name, but you have to understand that this is not actually what's happening. Okay, it's not actually what's happening. It's just this is how they described it back in the day. And this is the other thing to realize is that when they named everything, they really didn't know what was going on. This was all kind of brand new, and they're just trying to describe it using, I mean, just think about like Bohr's idea of the electron going around like a moon. Okay, no, that's not what happened, but it helped them visualize it, and then everything got kind of named after that. So same deal here with the spin angular momentum. All right, now what this thing is it's the exact same idea as the orbital, but now dealing with spinning. So think about the Earth going around the sun. So the Earth does 2 things as it goes around the sun. One is it just goes in a big circle around the sun, right? And here's the sun, goes in a circle. So that's the orbit. But at the same time, the Earth is spinning around like this. That's how we get days, right? That's why day and night happens, is sometimes we're pointing to the sun and sometimes we're pointing away from the sun because we're just spinning around like a top or anything like that. Okay, so when they were modeling this, they said, all right, well, if we've got electrons that are going around the nucleus like this, the electrons are also free to spin. So they call this spin angular momentum. Now, do electrons really do that? No. I mean, well, we don't know for sure because we can never actually see them closely enough to determine whether or not that's happening. Thanks a lot, Heisenberg, right? Uncertainty principle definitely blows that out of the water. But this was the model they used, and they realized that there is this quantum number called spin. We're going to see that other things have spin, protons, neutrons, all kinds of particles have spin. And so there is this thing called the spin quantum number, but that's what this guy S is. It's a spin angular momentum. Now, S is really boring, like really boring, because for electrons, since that's the world we're talking about, for electrons, S equals 1/2. Plain and simple. There are no other options. It's just 1/2. And this is weird too, because think about it. If these quanta are like countable things, why is this one a fraction? Right? That kind of seems silly. But we'll see later. Once we start talking about other particles and all these other characteristics that particles have, you'll see where that 1/2 comes from. But for right now, just go with, all right, electrons have an S, a spin angular momentum of 1/2. So in terms of the spin angular momentum, just like we had up here for the orbital, The angular momentum from the spin, we're going to call that capital S. It's equal to the square root of little s times s plus 1 times h slash. So it's really coming from the same formula. It's a different kind of angular momentum. So they called it spin angular momentum. Which, if you think about it, suppose you're coming up with this model trying to describe what's going on with an electron, and you realize that you need two different angular momentums. You're finding that as you're doing things. Oh, and by the way, the reason that they knew that there had to be angular momentum is conservation laws, right? We already know that, like, there are all kinds of things that are conserved, energy, momentum, right? But angular momentum is another one that's conserved. And through the interactions with these different particles, they saw that no, there has to be some sort of an angular momentum. And in fact, there had to be two different kinds. So imagine you're building this model and you go, oh, I need two different kinds of angular momentum. So I need two kinds of spinning, basically. All right, so we'll have the one spinning around the nucleus, and the other one is just, it's going to be spinning itself. All right, well, anyway, so that's what that is. And I apologize, capital S, little s. I know they look exactly the same when I write them, but that's we're going with the same kind of idea here as with the L. Okay, so since spin angular momentum really is kind of a nothing when we're talking about electrons, like, yes, it is a quantum number, but it's not one that we actually pay attention to or really care about because it's shared by every single electron in every possible atom. You know, they're all s equal 1/2.
I have a quick question.
Sure, go for it.
For big L and big S, is it times H bar, H slash,
Yes,
in the radical?
it's not in the radical, it's
Okay.
outside the radical.
Just making sure.
Yeah, so like this one, since the spin number is always 1/2, this ends up being the square root of 3/2. So you get root 3/2 H slash. So that one's always the same. And then you see root 3/2 and you probably get a little bit of excitement. And you should.
I did, yeah.
Because you recognize that from trig. But yeah, it kind of comes from similar places. But anyway. All right, so there's your spin angular momentum. So then there's MS. And this guy, again, I learned it as the spin magnetic number. But it actually is the same role as M sub L. It's the Z component of the spin angular momentum. That is definitely one nice thing about this naming scheme is that it's consistent as we go, right? So you see an M sub L and an M sub S. Oh, those are both Z components, just one is the L angular momentum and the other is the S angular momentum. All right, now M sub S can take on different values. Not a ton, but it can take on actually two different values. And it's either plus or minus 1/2. So basically this means that there are two ways that we can get our spin. It's either going to be spinning so that our vector is pointing, say, in this direction, or it's pointing in this direction. We have two choices. This one corresponds to the positive 1/2 ms, and this one's the negative 1/2 ms. All right, so there you go. Every electron in any kind of element, it doesn't matter what, is going to have these 5 quantum numbers. where 4 of them can vary. The 5th one is always the same. But there you go. Okay, now we've got these, yay. But here's kind of an interesting thing that comes from this. So the next thing we need to talk about is what's called Paulie's exclusion principle. And I'm going to guess that in physics or chemistry, when you guys talked about atom stuff, did you guys talk about Paulie's exclusion principle?
It sounds really familiar.
All right. Well, Paulie's exclusion principle is exactly why the elements build the way they do. Because what Paulie's exclusion principle says is that any two, I'm going to put here, like particles, meaning they both have to be electrons. They both have to be protons. They both have to be muons. They both, whatever, okay? They have to be alike. This isn't going to be, well, if you've got an electron and a proton, no, those are not like. But any two like particles in a potential well or trap must have different, a different set of quantum numbers. So it just means at least one of the quantum numbers has to be different. It could be that 3 are different, 2 are different, 4 are different. But basically, you just have to make sure that there's at least one difference in the quantum numbers. All right, and the argument for this actually comes from the wave function idea. Because imagine that you have 2 particles that have exactly the same wave function that are in some sort of a trap. What might happen there? What might happen if you have 2 identical wave functions?
They amplify by double or cancel each other out entirely.
Yeah, think about interference, right? There is the potential that they would just cancel each other out, which if we're talking about particles, what does that mean if 2 particles cancel each other out? No, that means they don't exist anymore.
Is it not sort of exist like just poof, gone, or is it like annihilation, like antimatter and stuff like that?
So would there be energy loss, or would energy be created? There absolutely would, right? So I guess I would say it is going to be similar to what we would talk about with like matter, antimatter. But this can't happen, right? We know that like there is more than one electron, say in a sodium atom, and we know they can't just cancel each other out. They don't just cancel each other out. They all live in harmony, right? They all live in peace and harmony. So this was the idea behind Paulie's exclusion principle, is that they must be in different states so that they don't actually cancel each other out. All right, well, this is what starts leading to what you guys who have taken chemistry know about things like the shells and things like that. All right, so let's just think about if you've got 1 electron. That 1 electron, let's just start easy with ground state. Okay, so this is going to be electron number 1. Electron number 1, it's going to be in the ground state, right? Because in general, the universe likes to stay in minimal energy, right? if you haven't figured that out from physics yet, let me just put it right out on the table. The universe tries to do everything with minimal energy. That's why I live my life the way I do. I'm just trying to emulate the universe. All right, so n is going to equal 1 because we want to be in the ground state. Now, that tells me immediately, though, that L has to equal 0. And M sub L also has to equal 0. Because remember, L can only be up to 1 less than N. Well, 1 less than N is 0. And then ML can only go up to plus or minus L, which means it's 0. And then in terms of MS, we actually have two different choices. We can have the plus 1/2 or the minus 1/2. So let's just say, all right, we're going to give it plus 1/2. So this combination of quantum numbers is now used. We can never, ever have another one that has this same combination. But you change any of them, any one of them, and we're still good, right? But you can't have any. All right, so we're basically talking about hydrogen here, right? The hydrogen electron in its kind of ground state is going to be here. Now, let's throw in another one. So here comes now electron number 2. Now, electron number 2 can't have this same combination, but really does want to have n equal 1. Well, here's the problem. If n is equal to 1, that then again forces L equals 0 and M sub L equal to 0. But luckily, we have another choice for MS, and that's the negative 1/2. So the second one is going to take in this value. But now we've used up every possible combination for n equal 1. There are no other choices. All right, so then if we go to a third one, the third one now is going to have to bump up into n equal 2. Now, what combination of L, ML, and MS it's going to have is going to be an energy thing, right? It will definitely come from energy, but in general, it is going to start with the L equals 0 again. So then ML equals 0 and MS equals plus 1/2. And then you're going to get the 2, 0, 0, minus 1/2. But then we can go even further with L equals 1. Okay, well, when L equals 1, now ML, we have all kinds of different choices. It can still be 0, but it also can be 1. It also can be minus 1. And then for every one of these, there's plus or minus 1/2. So I'm going to just be lazy here, again, emulating the universe, and kind of combine them. So check out how many we actually get to add when we get to the n equal 2 state. Well, there's 2 of these, another 2, another 2, and another 2. Right? So there are considerably more when we get to n equals 2. Well, all right. And then so on and so forth, and blah, 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 blah. All right, well, let me pull up a periodic table because I kind of want to show you, if you've not seen this before, let me show you why the periodic table is built the way that it is. All right, let me switch my screen here real quick. All right, so here's a periodic table. Now, first of all, you'll notice that the periodic table has rows. All right, each one of those rows is really corresponding to the different n levels, the different possible n's that we can have. So think about when we were at n equal 1, we had at most we could have 2 electrons in it. Well, the first electron gave us a hydrogen. The second electron gave us a helium. Okay, so that was that row. Now you go to the next row. I don't know if you remember, but we had 8 more that showed up with our n equal 2. Well, that's these 8. Right? And then we can go down further and we get, now we're into n equal 3. And then things start getting weird. We'll talk about that in a second. But it's basically, oops, I did not mean to do that. It's basically just structured such that these rows correspond to those different ends. And we're basically filling in, using Paulie's exclusion principle, all the different slots available for the electrons. All right, now in terms of where they sit in their columns, the reason that they're column like this is just because of how they behave with each other. We'll talk more about that later, I think, when we talk about nuclear bonds elemental bonds, chemical bonds. But for example, like this row here, or column here, where we've got helium, neon, argon, krypton. What's special about these guys to you chemist types?
Their valence shells are filled.
Okay, so
Evenly.
valence shells, just so everybody knows, that's their kind of their outer shells, right?
They're very unreactive.
Yeah, so their outer shells are filled, which means they don't react. They don't really form bonds with other things, right? They can, but it requires a lot of energy to do that and everything. So they are very stable for the most part. They don't interact with anybody else. So they have very similar properties, which is why those guys all come together. They're called the noble gases or the inert gases. Right? And then when you go over here, for example, like lithium and sodium, potassium, they all interact kind of similarly to each other because their outer casings look alike, right? And so that's kind of how the columns get formed, is that these things that share columns tend to react similarly with other elements, right? So that's kind of how those things broke down as well. All right, so when the physicists, and I guess they were chemists at the same time, right? We'll go ahead and just lump them all together. When they started looking at this, they started recognizing that there was order to it. The first person who kind of put this together was a Russian scientist by the name of Mendeleev. And he kind of was the first one to, I guess, invent the periodic table. Although I would argue that the universe invented the periodic table. He just sort of discovered its structure. But they were able to start piecing this together. And they were also able to use things like X-rays to piece that together as well. And we'll talk a little bit more about that in a second. All right, well, anyway, so here's how the different elements started forming. And the reason that electrons can only show up with so many in these outermost shells and stuff comes from the exclusion principle. I remember when I first learned chemistry way back forever ago, and they're like, oh, okay, so the first one's got 2, and the second one, you've got another 8. And I'm like, okay. Seemed like random numbers to me. But then when I took physics, when I got to college and I took physics and I saw this, and I was like, oh, now I see why there were only 2 in the first and why there are 8 in the next one, and so on and so forth. All right, so again, for those of you in the know, these are the the 1s, the 2s, all that kind of stuff. Those are basically telling you, if I go back to my whiteboard here, when we talk about, say, 1s, all right, well, that's n equal 1, and then s is the L equals 0. A 2s electron is one of these guys. a 2p electron is any one of these 6. Right? And then we can get the 3 S's and 3 P's, but then we can get 3 D's and so on. But an interesting thing happens when you start building this. Like the very first set you get are the 1s. And then you get the 2s and the 2p, and then you get the 3s and the 3p and the 3D. And then I think it's where this is where things start going awry. And I don't actually remember. So I'm since I'm being recorded, I don't want to just like start writing stuff down here. But I do know at some point they start coming in weird. Like you start getting some of the 5s before the 4s, or you start getting D's before P's, but D's that came from a different level. And so it starts getting a little bit more complicated than just this simple model, because remember the idea behind this very simple model was hydrogen, 1 electron doing its thing. Well, as soon as we start throwing other electrons in, they start interfering with each other. And I don't mean interfering like wave interference, although I guess technically they do as well. But they start affecting each other. Their presence affects the others. And eventually what happens is, well, again, the universe adds electrons in such a way that it's the minimum amount of energy needed to bump up to the next one. And when these start getting more complicated, when we start getting more and more electrons, it turns out that finding a slot for the next electron is sometimes easier going to a different spot, a different N value, a different L value than you're expecting. And the universe is going to do that. It's going to shoot for minimizing the energy. So for those of you who remember that from chemistry, the fact that you get some, like the number scheme starts getting mixed up, that's really why. It's the minimizing of the
It
energy.
never made sense to me.
I know, it's weird, right?
Yeah.
Where all of a sudden it's like, wait a minute, why did a 5 just show up? We're not even done with the 4s. But if you were to actually look at it, like go down to the details and look at how much energy is needed to reach that specific slot for the electron, you'll see that it's less than what it takes to, say, fill up the 4s or whatever it is. So it's very counterintuitive. Still, you see the details, and then it makes total sense. And you go, well, of course, it's going to try to do it with as little energy as possible. But yeah. Anyway. So I do want to point this out, though, that there is a nice little pattern to how many electrons you can get in each of these different states. Okay, so let me just show you really quick. So when n is equal to 1, so actually let's do this. So we're going to do, this is n, and this will be the number of electrons allowed. Okay, so when n is equal to 1, there were 2 electrons, right? It was just those 2 guys with the different spins. When we go to n equal 2, what we saw is there were the 2 with the 0, and then another 6 with the 1. And so that ended up being 8. Okay, now when we go to n equal 3, let me just sort of help you out here, and we'll do a real quick count of them. So what we're gonna just look at the NL ML combos, and then we're just gonna multiply by 2. Okay, so when we're at n equal 3, so we can have, so this is NL ML. We can have 3 0 0, 3 1 1, 1 minus 1 1 0, and we can get 2 2 minus 2 1 minus 1 and 0. So let's just count these up real quick. We've got 5 plus 3 is 8 plus 1 is 9. Doubled would be 18. So there are 18 possible in the n equal 3 realm. If we go to 4, we can speed this up a little bit if we just sort of steal this, change these guys to 4s, right? But by becoming a 4, we just added some more possibilities because we can have L equals 3, which makes ML 3 or minus 3, 2 or minus 2, 1 or minus 1 or 0. So when we go to n equal 4, we already had those 18. Right, we count those up. There were 9 of those. But then we just added another 7 here. So that's 16 times 2 is 32. All right, now, because I know you guys are all kind of mathy, I want you to recognize that this is 2 times 1, 2 times 4, 2 times 9, 2 times 16. And you can probably then make the at least assertion from the first 4 that it looks like the actual number of electrons that can fit in for any one energy level is 2n squared. All right, well, here's where I put on my math hat and I go, all right, prove it. I mean, we see that pattern happening, but is that pattern going to continue? Well, let's think about this. Forget about the multiplying by 2 for a second, because we know we're always going to be able to multiply by 2. Let's think about how many we're going to add on, because every time we go to a new level, we're going to get exactly what we just had. Like, you know, again, now if I'm going to go to n equal 5, I can just cross all of these out and go to 5s, right? So all of those are going to show up. But then I'm going to have to write down here, okay, well, now there's going to be a 5 with an L of 4 and, right? So we always know we're building it on top of what we had before. Well, think about what we're doing. We're increasing that L by 1 every time. So if we increase L by 1, that means the next set is going to have 2 more choices, right? Like when we went from L equal 1 to L equal 2, we added in these 2 options. When we went from 2 to 3, we added in these 2 options. When we go from 3 to 4, we're going to add in 4 and minus 4. So it's always whatever the other one was plus 2. So like here, there was 1, then we went to plus 2 is 3, plus 2 is 5, plus 2 is 7. So the next one, we're going to get 9. 9 more. Okay, well, if we get 9 more, then 16, that is 25. And I don't know if you remember this, but if you add successive odds, you always get perfect squares. 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 is going to be a perfect square. You probably saw that at some point in pre-calc, but that's just one of those kind of funky things about numbers. But anyway, because of the fact that ML can take on the plus or minus values, we're always adding the next odd, which then does mean we are always getting a perfect square that we're doubling. So kind of cool. Kind of cool that it works out this way, but every time we bump up another level, that next level is going to have 2n squared possible slots for electron. Anyway.
So I'm curious as to like how we depict evidence suggesting these things. Like this is all really mathy and theoretical because we can't necessarily see these things in action.
Correct.
So I'm just curious as to like, how do we know for sure that this is, you know, what's going on?
Like how do you know that, say, oxygen has 8 electrons in it?
Yeah.
And that they are in that whatever, wherever 8 fits in there. What is that going to be? 1s2, 2s2, 2p4,
Something like that. Yeah.
Okay, let's just say that. Okay, so how do we know that? Okay, well, we know that it has 8 electrons because things with 8 electrons are oxygen, right? Like that, it's sort of just by the naming scheme, you know, how it was built. But a lot of this we know by their interactions with other things. And that's kind of I know that's always a hard thing to wrap our head around, because like, especially in physics, when you're in the lab, you're used to just like, yeah, we watch that cart come and hit that other cart. We see, you know, and we know we can measure how fast this thing is going. But a lot of what we do is we infer, just like when we talk about astronomy, right? When we're talking about, you know, the size of another planet somewhere, it's like we don't have a scale big enough for Jupiter, but we can determine its size by looking at how fast it's going around the sun, and we know the interactions between gravities and blah blah blah, right? And so we actually infer that from other information. And the same thing definitely happens in chemistry. And I think specifically to your point of I mean, it's very mathy. We never actually see them, but we do see how they interact. And so, like when we talk about, let's say, like the particle colliders, you know, like down at Stanford or CERN, Fermilab, and that kind of stuff, where the particle accelerator, linear accelerators, and stuff like that. They create these things. They can actually strip stuff apart. I mean, they can break them down even further into things that you know, are not electrons, things that are smaller and weirder particles. But we never see those particles, but we see their effects, right? And so that's kind of like where all this comes from, is that, or why we quote unquote know, is that there have been a bajillion experiments that all point to, yeah, no, we keep coming back to the same set of information. But yeah, it is unsettling, because we want to be able to like actually just like look at it. We want to look at an oxygen, and we want to be able to look at all 8 of those electrons and read, like, what we really want is to be able to look at that thing and it has printed on it, like on our foreheads, right? If it just went N equals 2, L equals 1, ML equals 0, you know, like that's what we want, but we don't have that, right? And we don't actually know what any one electron is. Like, let's say we strip an electron off, even if we could, and like target it and see it, you wouldn't know which of the ones you just stole. Because what's going to end up happening, well, you would be able to tell if a photon was created that showed that jump and whatnot, right? But we wouldn't know which one we stole, because everything sort of like reshifts. You know what I mean? Like they all end up kind of taking the lower energy ones. They all slide down, you know, as necessary to fill in the missing gaps. But our naming scheme, our numbering scheme, is really just a way for us to keep track of where we are, even though specifically is, okay, well, is that the one with the upspin and the next one is the one with the downspin, or vice versa? I don't know. Doesn't really matter, right? We just have to have them named in some way. So I feel
Yeah,
like
I guess it's just kind of I guess it's kind of like just a pill you need to swallow.
a little bit, but it's not like it's based on nothing, you know, like, because there are different kinds of pills that you have to swallow. There are the ones that are just like completely out there for no reason, and then there are the other ones that are like, yeah, I know this feels weird, but we definitely know that it works this way. And that's kind of where we are now, right? Like, do you guys know about quantum entanglement?
A little bit.
Maybe let me talk about that a little bit. This is an appropriate time to do it. I don't know that they actually ever talk about it in the book, but um, this is as good a time as any. Let me just go ahead and stop share here for a second, so a little bit bigger. Okay, so this quantum world is weird as shit. I mean, it absolutely is. There are so many weird things. I mean, like, just go back to Schrodinger's cat, right? Like, how just messed up is that? That you don't actually, that the cat is alive and it's dead. It's both. And it will stay both until somehow it's measured and then it's determined which side of that barrier we're on or whatever, right? Okay, so that's weird. But it appears that that's how things behave, and so we model it that way. Well, here's another weird one. So quantum entanglement is this. When you have particles that, like, let's say we create two particles from one, and so we maybe have some bigger particle and we break it into two pieces that are identical. All right. Now we already know from Paulie's exclusion principle that they can't quite be identical. They have to have some difference in their quantum numbers, right? But they are going to look exactly the same. They just have different quantum, some different number in their, or some different combination of quantum numbers. Now, here's what we find, and is that if you affect one of them, it affects the other because of the exclusion principle, right? Like, what if I've got these two particles and I change the angular momentum on this one so that it now matches this guy? Well, we know that that can't happen from the exclusion principle. So we affect this one and there's an instantaneous effect on the other. They make sure that they are in different quantum states by Pauli's exclusion principle. Yeah. All right, so here's where this gets weird now. By all accounts, it is instantaneous.
Which probably freaks Einstein out.
Okay, so now think about what this means. Now that means there's some kind of communication, right? There's some kind of communication between these. The fact that when we affect this one and the other one feels it, right? Now this is getting into that like weird, creepy twin thing, right? Where twins just kind of know what's going on with the other. But so this one gets affected. All right, now this other one immediately goes, oh, okay, I need to change. I need to react to it. Well, if it truly is instantaneous, that communication is happening at faster than the speed of light. But we can't have anything going faster than the speed of light. And while the math suggests that this should happen, you might go, okay, well, that's just the math says that this has to happen. But we've done it. This has been done. That they've been able to affect one particle and see an instantaneous effect in its buddy, twin, whatever we want to call it. That's actually occurring. Okay, so this is trippy, but it's got amazing potential for use, right? Because just think about this: if we could create some sort of a computer something or other that's built off of this. So here's what we do: we send some particles in whatever container in a ship going to Mars, and we keep the buddies here on Earth. What we can do is affect the ones on Earth, right? Like, so I poke particle A, like poke, poke, poke. They're going to see in their spaceship, we'll call them A prime. Particle A prime starts going, whoa, I'm getting poked. Instantaneous communication. We wouldn't have to worry about the time lag anymore, right? We could be across on the other side of the universe and be able to communicate immediately, right? That would be insane. That would be completely insane if we can figure out a way to do that. And we haven't yet, right? And this is definitely, I'm not saying I'm part of any of this experimental group. This is the we as humans, right? But I agree, Victor. He just said that in the chat box that this is crazy. It is crazy. It is absolutely crazy that this happens. So what this tells me is that I forget, somebody a while ago was asking, I think it was probably Bradley, if I thought that there was a better model or the model was incomplete or something along those lines. And this specifically, quantum entanglement, is for me what tells me, yeah, we don't have the whole story. There's definitely something else going on that we don't know about, or don't have a good handle on. But when we can figure that out, then that's that next revolution. So that'll be one of you guys. And then make sure that when you're giving your speech for your Nobel Prize, you just give me a shout out. That's all I need.
I'm curious as to whether or not gravity plays a role in how particles interact with each other.
Probably. I mean, obviously, there is a gravitational force between particles. Is that what you were getting at, or are you saying like, if we've got two particles that are in a gravitational field of another object?
Yeah, that's what I was alluding to. I didn't even think about the gravitational attraction between the particles.
Yeah, because I mean that automatically is there. That one just tends to be, well, gravity is actually a very weak force. Believe it or not, I know that we tend to think of it as kind of a big important force, because in our world, gravity is probably the force that you experience the most. Right, every day as you're walking around, even just sitting here in your chair, you're experiencing gravity. But gravity is actually really, really weak. So even when we start talking about, say, two electrons interacting, that the gravitational force between them is so small relative to like the electromagnetic forces that you can kind of ignore it. And so if we go to the, which I think is really the heart of your question, Bradley, which is okay, I've got these two particles and they're experiencing gravity from the sun or whatever. Is that going to affect them? It will affect them, obviously, but it's going to be pretty small and, quite frankly, pretty insignificant compared to other things. In terms of quantum entanglement, like, does that affect the communication between them? I don't know. I doubt it. Because as far as I know, this quantum entanglement, I mean, it's existence. Just existing is being subject to quantum entanglement.
I just thought of an experiment. I don't know how it would happen, but to test to see if it's real, quantum entanglement is really instantaneous, maybe you would want to get two quantumly entangled particles and then shove one of them into a black hole.
and see what happens.
Yeah.
Well, that if you could do that, that would definitely help answer the what's it like in a black hole, right? Because you could at least see what the effects are on that particle that you just sent into it, and you would be able to see the corresponding effects on the one that you've got. Yeah, that's definitely a way to determine what's going on inside a black hole. That'd be cool. Never mind that we got to get it to the black hole, but
yeah, that's the different issue. Like, and then what if you get too close and you're just screwed in general?
Yeah, details, right? As they say, was that saying that the devil is in the details? That's definitely what we're talking about here, where it's like, yeah, but it's a great thought experiment, right? And that's how we end up getting these actually kind of cool things happening as you start going, all right, well, I can't quite do that. How can I, change it or whatever?
I have one more for you.
Yeah, go for it.
When you said you were going to show us a quantum number, another one,
Uh-huh.
I thought it was going to be 4-dimension quantum
Oh,
number.
sorry to burst your bubble.
It's okay.
And then so Victor just put in the chat box, he says, so if telepathy exists, this is the way. Potentially. So obviously, me being a science guy, when it comes to things that are more like supernatural, I'm always a little bit skeptical, but I can definitely see telepathy being really there. That they're like, think about this. We all have different ways of perceiving the world, just plain and simple. We all have different abilities. Like, I don't see nearly as well as other people. That's why I need these, right? To help me out. Now, imagine I don't have these and I see the world in its grand fuzziness that it is right now. Like, this is how bad it is. I'm looking at my computer screen. I can't read a single thing on it, like your names or the chat box or anything. So this is actually, when you want to mess with me, you can type random stuff in the chat box and I'll never know what you just wrote. Suckers, except it gets saved. No. All right. Anyway, so I'm looking at the world in this crazy fuzziness. Now, I'm talking to somebody else next to me and they go, "Oh my God, did you just see that?" They point up into the sky and I look up at the sky and I'm like, "No, I don't see anything." Like, "What? You don't see that? You don't see that thing flying around?" I'm like, "Dude, I have no idea what you're talking about." Right? I can't observe it just because of the limitations in my body. Now, this sight one, this might be a little bit extreme because most normal people, there are enough normal people out there that all kind of see the same thing. But I'm sure that there are people that have better sight, even like just like, we'll call it superhuman sight. So why can't there be other things that I just don't see that are actually out there, right? So when it comes to things like telepathy or telekinesis or anything like that, even ghosts, I am perfectly open to the possibility that there are ghosts, that there's this other existence that most of us don't see, or you only get a glimpse of occasionally, because it's true about all the other senses. There are people that are really good at tasting. There are people that have really exceptional hearing. Well, why can't there be people that have really exceptional, whatever, thought receptors, for lack of a better word, right? And I kind of feel like they do exist, because have you ever noticed how sometimes, like, you'll be having a thought about somebody or something and then they kind of like turn and look at you? I've definitely had that happen. I'm like, whoa, how the hell did you know I was just thinking about you? But I don't know. But yeah, it could even be some sort of a quantum entanglement kind of thing as well. Basically, the more learning modern physics and reading about modern physics made me realize that we don't know shit. We don't know anything. We're grasping at straws. We're making models. I mean, we're talking about electrons spinning around like a top. Come on, right? But we're doing our best to put it into words that we understand and that we comprehend. But I'm convinced that there's a little bit more framework to this universe that we are very unsure of or unclear on.
Anytime I have that like weird experience of any of those sorts, I always call it a disturbance in the force without fail.
Yep, it's very true. And then of course the Matrix gave us now the, oh, that was just a glitch in the program. right? I like to use that one too, where I'll be like, oh, we just ran into a little bit of a glitch. So, anyway, I honestly don't remember what I was talking about now, but that's all good. So quantum entanglement, right? Something along
So
those lines.
Professor X, he quantumly entangles himself with everyone and then communicates via that way.
Or he's found a way to read, to see, let's just say, call it see for lack of, we'll just say see as in like be able to measure somehow. He's actually able to see waves that are at frequencies that nothing else can see. Like maybe even their frequencies aren't, maybe they're like imaginary frequencies. And when I say imaginary, I mean like imaginary number frequencies, right? Like what if there's a whole set of waves out there that have like imaginary frequencies that, maybe they're the ones that describe our thoughts or, other stuff like that. And, finally someone's able to tap in and see those frequencies. Just like when we were talking about, right, like the Balmer series and all that sort of stuff, where, they only saw some of the wave drops or the wavelengths from the energy drops, because those were the ones that were visible, but there were a whole bunch that were invisible. Maybe the whole world is like that. And so when we talk about the wave function of particles, well, we're describing just the ones that are visible to us. Visible meaning we can measure their effects, right? We can see things like barrier tunneling and all that, but maybe there are other wave functions that we just don't see. That maybe these electrons actually have multiple wave functions. There's the real one and there's the imaginary one. I mean, who knows? So, but this stuff is cool because it makes you think about that. It makes you really start looking at it and being like, all right, well, maybe all of these things that we just assume are true are not. Maybe these experiences, well, maybe they're only experiences to us because of our ability to measure and interact with the universe, and maybe there's more out there. And it ends up being philosophy class, right? I mean, if you think about it, what we're talking about here is philosophy. What's the nature of the universe? What's the nature of life? Are we really just looking at the inside of the cave and we're watching the shadows go by, and that's what we think is reality? Well, when there's actually stuff behind us, well, maybe we're looking at the shadows. And if you have no idea what I'm talking about, that's a philosophical thing, the cave allegory, which is that all you're seeing is the projection of reality from behind you on the wall, right? Like imagine you were in a cave and all you've ever seen is just ahead of you in the cave, and then there's a big bonfire behind you or whatever, and people are walking past. You'll see their shadows on the wall, and you'll see those shadows interact, and you'll see, the kid playing catch with his dad, like whatever, and you'll see the shadows of that, and you start to think that's reality, when really that's not reality. Reality is going on behind you. You're just seeing the results of real life. Well, I think that was Plato, Ralph. I think, but I'm not 100% sure. Okay, so what about this existence? So we're talking about, this quantum entanglement. What's to say that what we're really seeing is just the shadow of something else, and we see it as quantum entanglement, where if we could turn our heads around and see reality, we go, oh, that's really what's going on, right? Which again kind of gets to the matrix idea too, right? Like you're in the matrix, you're living in a computer simulation, but it seems real enough to you because that's your experience, when in reality there's something else going on, right? So
Or that made me think of, well, what they call dark matter.
mhm.
Because I mean, we see its gravitational effect on a galaxy, yet it's not there. You
Yep.
know?
There's
Maybe-
missing mass.
Yeah, and maybe the matter we see is the shadow you're referring to. You know?
Yeah,
And it's
maybe.
it's just weird to me. That's the other thing too, with from what I understand, anyways. Like, ever since this whole quantum theory started coming out, physics is kind of plateaued, and I think it's solely just because we're limited. You know, it's
Limited
interesting.
with what we can see, and
Yeah, and observe exactly.
yeah, and and it could end up that this is where we stop. That like we just don't have the ability to turn our heads around and see what's actually creating the shadows, right? And maybe that's the question that will never get answered. um I forget what it was. Oh, okay, yeah, it was the Indiana Jones movie, the most recent one, the Crystal Skull one, right? The dumpster fire that was that movie. um but remember when, if you saw it at the end, like they meet the aliens, and the one, she's just like, I want to know everything, tell me everything, I want to know, right? And that's kind of where I am. It's like, I want to know, I desperately want to know, but I realize that I will never know, right? Like I think the universe is so amazingly complex, um, that we'll never actually see it all. So, but anyway, enough for philosophy. Let's do a little more physics, because I definitely want to wrap up chapter 8 today. So let me just tell you a little bit more about some funky things that kind of came up from looking at atoms and these elements and trying to order them, and all that. So we can talk philosophy some other time, and I'll be more than happy to do that. You guys know me, get me talking, and I never stop. All right, so some other things that were kind of discovered along the way. In terms of the quantum numbers, they found that something kind of interesting happened. Um, Obviously, the big jumps we know about are the jumps in n, right? And those are evidenced by the wavelengths of photons that are produced. And so there are some byproducts of that I kind of want to talk about here real quick. The first is X-rays. Now, I imagine, I mean, you guys all know about X-rays, and I imagine that just about every one of you has had an X-ray at some point, whether for a broken bone or for dental work or whatever. But have you ever thought about how they actually make X-rays? Like, what is it about that machine that when they, stick it up against your jaw here, and then they leave, and you hear the button get pressed, and you hear a little bit of hum, and then they're like, okay. And meanwhile, your face got bombarded with X-rays. Have you ever actually thought about how they make that?
Like,
Now I'm
how-
guessing that has something to do with drop in energy levels.
Okay, so clearly, spoiler alert, right? So obviously, we've been talking about this now for a while, but again, as a kid, I don't know, it's just an X-ray machine. They think you broke your hand, you go and you stick your hand on it, and okay, well, so I'm guessing most of you have not thought about it, but it truly is from these energy drops, and these are some of the invisible energy drops. So think about this. What do you know about X-rays? Do you know anything, like, what do you know about them in terms of like their wavelengths and all that, or frequencies? Anything? That's like a legit question.
I want to say it's on the lower end, correct?
It's actually higher than visible light, I thought.
Okay, so when we say lower or higher, it depends if we're talking about frequency or wavelength.
I was referring to wavelength.
Okay. And what about
Yeah,
you,
I was
Jason?
referring to frequency. So
Okay. So then those go together, right? Small wavelength means high frequency. So, and that actually is the case, right? With X-rays, these have a very small lambda, which means they have big F. Okay, well, when they have a machine that actually produces X-rays, they are making use of energy drops. Remember how the energy is related to frequency? I hope it was E equals H times F. So X-rays occur when there's a large energy drop. So we're not talking like from n equals 5 to n equals 1. We're talking big energy drops. So in order to actually produce them, you need to get these things excited so that they're up in a much higher energy level. All right, well, that's why they have to actually be plugged into the wall, right? That we need electricity and all that to make them. So of course we're talking about the non-naturally occurring X-rays, because naturally occurring X-rays occur as well. Anyway, so they require a large energy drop. So there was a guy, I forget his name, and I'm really sorry I forget his name, but was doing an experiment looking at trying to classify elements. And so he was basically giving them energy to get them excited so that they would release X-rays. And then he could look at the frequency of those X-rays to figure out the kind of energy drops that he was getting. And what was really kind of cool as he was doing this, he realized that there was a relationship between the frequency and the atomic number. I don't think we've talked about this yet. So let me just get it out here. So the atomic number, we're going to use the letter Z to represent it. And what Z is, it's equal to the number of electrons or the number of protons, either way you want to think about it, in the atom. Okay, so not in an ion at all, but just in the atom itself. Because they end up being neutrally charged. So there's always a proton for every electron, unless it's an ion. So, but anyway, so Z is just the number of electrons or a number of protons. So like hydrogen, Z equals 1, Z equals 2 is helium, 3 is lithium, and so on. Those are the little numbers that are in the corner of the squares in the periodic table. All right, well, what he saw was that there was a total relationship between these, that the frequency that he was getting was actually equal to Z minus 1 squared times a constant. So it's right as K times Z minus 1 squared. And he basically did this with elements that he knew, right? So imagine it's like, okay, I've got gold here. I'm going to bombard gold with this thing, or I've got oxygen, or insert your favorite one that is known. And so they already knew what the Z number was for a lot of these. And so he basically plotted them and saw that there was this relationship between Z and F. Basically, there's a linear relationship between Z and the square root of the frequency. So then, noticing that helped them find other elements. Because now we've got some random thing, we don't really know what it is, let's bombard it and create these X-rays. You read the frequency of the X-ray, you can go into this formula here and then determine what Z needs to be. And so this guy, man, I really wish I remembered his name, but he ended up discovering like 30 some elements using this method, using the X-rays. So another case of using this frequency that comes from the energy drop to get some information.
And this is, I'm guessing this is how they figured out that stars made the elements, huh?
You mean that like you don't mean that the stars are made up of elements, but that they actually create.
They actually create, like they looked at a nebula that just, that's post nova, and then saw the different elements, and then they thought, oh my God.
Yeah, where else could it have come from?
Exactly.
Yeah, I think you're probably right. I actually haven't studied much on the history of stellar science, so I'm not certain, but I wouldn't be surprised if that's exactly how it kind of played out. That once they started figuring out the idea of spectra and all that kind of stuff, and were able to measure those things, and they start recognizing, oh, whoa, there's gold in that nebula, right? Or whatever. I think you're probably right. There's gold in them, our nebulas. All right, so here is another consequence of this quantized energy. Another fun one is fluorescence. Do you guys know what that is?
Are they noble? Are they higher on the noble gas? Like in an atomic number?
What do you mean?
Like, are the fluorescent atoms noble gases on the order of like higher magnitude of atomic number?
That I don't know.
Okay.
Because go ahead, Jacob.
This is the principle that makes glow-in-the-dark paint glow, right? Like it absorbs light and then releases it later by fluorescing.
Okay, so fluorescence is it's basically the release of color that comes from getting excited, these things getting excited. Examples of fluorescence, and Jacob gave a good one. So glow in the dark. You also see it in minerals. You actually see it in some animals. Animals have fluorescence as well. Things like this with the animals and minerals and stuff. This is where, like, black lights. You guys know about black lights? This was actually really, really popular when I was a youngster. The black light posters. You had these like felt posters that then when you shine the black light on, instead of being boring, just black and white, and they had all kinds of trippy colors. Look, it was the 70s. It was a weird time.
Don't worry, I have one in my room.
All right. So I guess retro, right? Everything that's old is new again. But there are certain things that when you shine, say, black light is ultraviolet, basically, is what we're talking about when we talk about a black light. It's UV. Because you don't really see it, right? It appears black, but there's still light. But the idea here is that when you shine a black light on it, you are giving it energy, right? And think about this. If we're putting ultraviolet, this means that this is larger F than visible. Right? Ultraviolet means it's shorter wavelength, which means greater frequency. Okay, well, that means that each one of those photons is carrying more energy than any of the visible light. And I didn't really talk about this, but when you want to jump up a level, you can only jump up a level if you catch a photon of the exact right amount. Okay, so like let's say here are energy gaps. Okay, so there's some energy gaps. If I want to jump from, say, n equal 1 to n equal 2, I have to catch exactly this change in energy. If you send me a photon that has more energy than this, I can't do this jump. Because remember that these are chunks of energy. These are I like to think about them as like denominations of bills, right? Like if you just say, hey, can I have $1? If I don't have $1 bill, like, no, you can't have $1. I can give you $5, but I can't give you $1 because I've got the wrong denomination. Okay, so it's the same kind of thing. To bump up this energy level, guys like, hey, I need $1.37. I don't have $1.37. I have $2.15. Oh, that's too much money. I can't jump up this level. So it's the same kind of thing. So it goes both directions, that when we drop energy levels, we release a photon of that frequency, but to jump up, we have to absorb a photon of that frequency. All right, so let's just think about this for a second. So we send in ultraviolet light, which is going to have, let's say that this bottom one is a visible wavelength. So it's something we could actually see. Well, what will happen when you shine a black light onto minerals or certain animals or posters in your, 70s throwback room? What ends up happening is you'll get these particles, but they'll jump up higher. Okay, so let's say that the ultraviolet brings us so that we're up here. Now, we shine that light, we get a whole bunch of things that are up on this higher level of energy. And they, of course, are going to come back down to ground state because they want to. They want to minimize energy. Now, some of them will do that whole drop all at once. They'll just come back all the way. But as we saw before, and I think we talked about this before, like when we were talking about Balmer and Lyman and Passion series and all that, is that, well, some of these are going to drop a bit down here maybe, and then another jump. Or maybe there's another one that does just this little jump and then the big jump. Or maybe there's another one that does this jump and then this jump and then this jump, right? So you get all kinds of bouncing around. Well, if, let's say the one that I was talking about, from n equal 2 to n equal 1 is the visible one, the one that we can actually see, we shine a black light, and what's going to return is a color that's not black light. We're going to see the purples and the yellows and the greens and the blues and the reds, all depending upon what that level is. So when you shine a black light onto a rock and you get all kinds of funky colors, that's because whatever the mineral composition is, it has elements that are getting overexcited by the ultraviolet light, and as they're returning back to the ground state, are producing visible colors. So like I know butterflies have this a lot in their wings. You get some color schemes on that. Like scorpions, I know that you can actually see them if you shine black light. If you ever go wander in the desert where there's scorpions, carry a black light. My grandparents used to live down in Arizona, so we would go wander the desert all the time, and we always had the black lights. We had a black light flashlight just so that we could help see them, because you don't want to, get into scorpions if you can avoid it. Anyway, so that's fluorescence, which is another byproduct of this dropping energy levels. And glow in the dark is really the same idea. It's just those materials that glow in the dark, they tend to store the energy longer. It takes longer for those all those excited particles to come back down to ground state. So they'll last longer. But if you've ever had glow in the dark anything, that's also why the longer you have it under light before you turn off the lights into the dark, it stays brighter longer, because you've excited more of them. But those are usually created chemically with whatever the paint is designed in such a way so that it will absorb visible spectrum and release visible spectrum, but also release it very slowly. Anyway, so there's another byproduct of this jump of levels.
I have a quick question.
Yeah, go for it.
Does this also relate to why some materials, hold, thermal energy better, more efficiently than others?
It can. And that's going to be more probably if it's absorbing or releasing infrareds, right? Those tend to be the ones that do that. I'm going to say yeah, because thermal radiation really is the same thing, right? It's releasing invisible photons. And so just the structure, the chemical structure of whatever that material is such that it's going to release non-visible, but now smaller frequency. But yeah.
The reason why I asked is because I was thinking about hot sand versus the ocean, or I guess at least the ocean I've been to, versus Tahoe beaches. Tahoe sand gets so stupid hot because it's silicate. It's like a bunch of silicate rocks. And then if you go to the ocean, or at least where I went, sand was warm, but it wouldn't burn your feet like Tahoe sand does.
Uh-huh.
And I'm just made me think like maybe the different material.
No, it definitely
for
is.
that.
Different materials will absorb the energy differently. And some of it's color, right? Like also think about Tahoe beaches are a lot lighter in color. Or you have difference between dark and light. Because like dark beaches tend to get hotter as well. And that's totally because of the fact that they're absorbing all of the energy. Because if it's black, that means you're not seeing much get reflected off of it. So that means all that light is being absorbed, right? So that's why dark things end up being hotter in general than light things. But Tahoe sand also sucks because it's really sharp. That decomposed granite that's pretty sharp stuff. It's not like lava sharp, but anyway, yeah, this stuff is everywhere if you really look at it. All right, so here's one more, and this is one I know you guys have all been dying to talk about. Let's talk about lasers. Because lasers exist 100% because of this energy jump between states. So I don't know if you know what laser actually stands for. It's an acronym like NASA or SCUBA, but it stands for light.
SCUBA's a acronym?
Self-contained underwater breathing
Self-contained
apparatus.
Wow, I didn't know that.
Yeah. So hold on. Here's a light amplification by stimulated emission of radiation. Okay, so this is what laser actually stands for. Light amplification by stimulated emission of radiation. Laser definitely sounds cooler. It's a mouthful anyway. All right, well, if you just kind of break this down, okay, so we got light amplification. Well, if we amplify, it just means we're making it brighter, we're putting out more of it. And we're doing that by stimulating, so we're going to give it just a little bit of a boost, the emission of radiation. So whatever this material is going to be sending out radiation, sending out photons. Okay, so here's how lasers work. Lasers are going to, whatever material we've got that's creating our laser, And there are a whole bunch of different kinds of lasers, by the way. They tend to be gases, but they can be lots of different things. But so we've got a ground state, and then let's just say that this is our first excited state, or it's an excited state that's producing what we want. Okay. So obviously, just like before, if we know what this change in energy is, it's going to give us our frequency. So let's take like one of the red light lasers that we use all the time in lab. That's one where that energy drop is going to be such that the frequency gives us the red light. I don't remember. I want to say that those in lab, they're around 650 nanometer wavelength, I think. It's been a while since I played with those lasers, but anyway. All right. So how does this stimulated emission of red, how do we get light amplification from this? Well, obviously, if we get things excited, they will then drop back down and give us a photon. But the reason lasers work is that with the right kind of materials, and that's why this only works for certain materials, what'll happen is we send in a photon. So I'm going to send in a photon here. Now, that photon, because of resonance, is going to take some of these ground state particles and excite them. Right, so remember resonance, where everything kind of has its natural frequency, but then if you are supplying a forcing function at that same frequency, it causes it to get more and more and more, right? We were talking about that in diffie-Qs. So it's the same kind of idea here. All right, so we just sent in a photon and it got, some things excited. And even if it's just one that gets excited, think about then what happens. So this photon, this is still photon number one. So we'll send photon number one is going to keep going. But then let's say that this particle drops back down. It's going to create another photon. Now I'm changing its color just to designate that it's coming from that other particle, but they're actually going to be the same color of light, right? They're going to be exactly the same color of light because of the fact that this energy drop is the same. All right, well, now we've got two of these photons cruising through. And each of those photons now has the possibility of exciting some of these particles by the same manner and causing them to jump up. Well, if they excite some more, so let's say we excite yet another one here, we'll make this guy yellow. He gets excited and then drops. Now we've got another photon and so on. And so we are amplifying the light by stimulating the emission of radiation, these guys, so we're helping it out, but we're doing it by supplying photons as kind of the seed. We're priming the well, we're just giving it that extra little boost to make them start. So that's what's really going on with lasers, is that the photons that are being created are helping create more photons.
So it's kind of like a domino chain a little bit.
Absolutely. Yeah, it's the same kind of thing. And we'll talk about this like when we talk about nuclear reactions later. It's the same sort of thing that, okay, so this now impacts these, and then the next thing you know, boom, 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 it builds. All right, so this is why we got to actually plug it into a power source, because the power source gets the first ones excited. As they start dropping and creating more photons, that sort of helps them, build and build and build. But some other kind of interesting things happen with this. One of them we've already kind of talked about. It turns out that this is monochromatic. That's just the fancy way of saying the same color, which means, of course, same frequency. So it's the same color light. So it's monochromatic. So like think about those lasers, those red lasers. You only see red. You don't see other colors, like when you turn on a light bulb and you see a whole bunch of different colors. Okay, so it's monochromatic. But the other thing that's kind of cool about it, except that might help if I spell it right, it's coherent. It's coherent light. And what this means is that it's all in phase. And that's why lasers end up being really good for things like the double slit experiment, because that light that's coming out, all of those photons are exactly in phase with each other. And that's a byproduct of this resonance thing, like how those photons are being created, that they're getting created by the other ones, as they end up being coherent. So they're all in phase. But again, this is due solely to the fact that energy is quantized, that there are these discrete chunks, right? So to kind of get back to something Bradley was asking about earlier when he was like, well, how do we know? Right? Well, it's this kind of thing that we can create lasers, and the only way that they can work is if we have finite chunks of energy. And so this model definitely explains a ton of what we see. So much so that it kind of feels like it must be right, or at least it's as right as what we can say right now, if we go back to our previous discussion of the cave allegory.
See, that blows my mind too, because then it just, I wasn't trying to be like pessimistic or like, oh yeah, how do we know though? It's just like, obviously it works, but then the question's like, what's missing?
Right.
No,
totally. And just so you know, I didn't take it as you were, being, shitty teenager type, right? With the whatever, right? No, I didn't take it that way, because no, that is absolutely a legit question, because it is like, it is so Wizard of Oz, right? Wizard of Oz, when it's like, ignore the man behind the curtain. What the hell is the curtain? I mean, we see the great and magnificent Oz, but what's pulling the strings? What's actually making it happen? And
that's the Mad Hatter, which is a whole nother thing.
Yep. Like, man, did we just get back to philosophy again? Holy crap. Right? Like, you can't it. But I'm convinced, and I think I told you guys this, that I see science, religion, philosophy, it's all really the same thing. It's all trying to answer the same questions. It's using slightly different methodologies. It's, but it's all coming down to the question is, what is existence? What is this thing we call life? Right? And you're approaching it in different ways, but we're all that question. And they start intertwining for sure, especially when we start getting into this quantum world where we literally can't see it because it's impossible. Right? So
I have a question for you.
Yeah, go for it.
So mathematically, even in our experiences, we've seen waves in 2 dimensions, like on Desmos. We've seen them in real life,
Yep.
The ocean, the lake. Is there a mathematical model of how a wave might look in a 4-dimensional plane?
Probably.
Do you know of any?
I've never looked into it. No.
Okay.
No, dude, my work with waves was like tides. Beyond that, I don't care about some fourth dimensional tide because it doesn't exist. But yeah, so I'm sure there are. I bet if you just did a little bit of internet diving, you would probably find something about four-dimensional waves. But I've never looked into it, so I have no idea where to even begin. So I'm not gonna.
Definitely. The reason why I asked, I was just thinking, like, what's that thing that behind us? And I was thinking maybe it's a dimensional thing.
Yeah.
Because we are limited in that respect too.
Yeah, and I actually think that's probably a big part of our issue is that we are definitely trapped to our coordinate world, right? I mean, our three-dimensional world, even if you want to go to 4 dimensions with time, which I don't really like to do because time doesn't work like the other dimensions anyway, right? We can only progress in the one direction in them or in it. But it's like, yeah, no, we are restricted to seeing the world that we live in. And we you literally can't see more dimensions, right? Like imagine a 2-dimensional creature, like in Flatland, they would have no idea what 3 dimensions means because it doesn't exist in their experience, right? So yeah, maybe there's maybe a lot of what we see as supernatural is just the other dimension creeping in every once in a while, or people that are attuned can catch a glimpse of these other dimensions, or who knows.
Yeah, I'm curious if we can we like affect lower dimensions? Is that a thing?
When you say affect them, what do you mean?
Like, suppose I had a piece of paper and there was flat people on the piece of paper. Would I be able to like do things to their universe?
Probably.
Even in a higher dimension?
I mean, you could probably, well, we do stuff, put stuff into 2 dimension all the time. Think about when you are writing on a piece of paper. You just created a line. Now I know technically it is 3 dimensions because there's the thickness of the graphite and all that. But I mean, if there were creatures that lived on the paper and all of a sudden you introduced a line. Yeah. So maybe all this stuff is just multi-dimensional creatures that are just messing with us. Some little like bratty 5th dimensional kid. It's like, I'm gonna mess with these guys, make them think there's aliens. Yeah. I'm just thinking about me as a kid because I would have been that kid.
The reason why I thought about that is my kid is always playing with ants, and I'm curious if ants are aware that there's 3 dimensions.
The ants definitely know they're 3D. That they have to, seeing they like when they create their tunnels and everything, they go 3-dimensional. I think they must have a decent perspective, 3D perspective, but I don't know. Not an ant. Nor if I studied them, but I bet they do. I bet they do. All right, guys, I think this is probably a good place to stop. So we'll go ahead and call it a day. Yeah, just don't forget that there's still some homework to be done. We're not going to do a quiz this week. Actually, hold on. Maybe we are. We have an exam set for next week, right? Let's do one more quiz. We're going to do a quiz on Thursday, and let's make that on, chapter 7. You guys are working on that homework anyway. So we'll do a quiz on Thursday on chapter 7. So we'll actually start in here at, what is that, 4:40? All right, so look for the quiz to pop up on Canvas, available at 4, and then we'll get going in class at 4:40. All right, so anyway, so we'll do that on Thursday, and then we'll move into the next chapter and start talking about how all this energy stuff makes matter do what it does. All right. So with that, I'm going to go ahead and stop our recording and wish you all an awesome couple days.